Mem0, the memory layer that lets AI agents truly remember. Part 1. The concepts. Why AI agents forget and how Mem0 fixes it with a dedicated memory architecture. Large language models are stateless. Tell your assistant today that you are vegetarian and avoid dairy, and it answers perfectly. But start a new session tomorrow, ask what to cook for dinner, and it happily suggests chicken Alfredo. The context window is finite, and once information falls outside it, the model effectively resets. Bigger windows only delay the problem, because attention also degrades over distant tokens. Mem0 is a memory layer that sits between your application and the language model. As the conversation flows, it extracts the salient facts, consolidates them against what it already knows, and stores them in a vector database. When the user comes back with a question, the relevant memories are retrieved and injected into the prompt. Instead of replaying an entire history, the model sees a short, dense summary of what actually matters.
Here is the extraction step from the paper. Each new exchange is a message pair, the previous message and the current one. Mem0 builds a prompt, P, from 3 ingredients: a rolling conversation summary, S, for global context, the last M messages for local context, and the new pair itself. An extraction function phi, implemented by the LLM, maps that prompt to a set of candidate memories, omega 1 through omega n. Salient facts in, structured candidates out.
Extraction gives you candidate facts. The update phase decides what to do with each one. Mem0 retrieves the top most similar existing memories from the vector store, then asks the LLM itself, through a tool call, to pick one of 4 operations. Add creates a brand new memory. Update augments an existing one with complementary detail. Delete removes memories that the new information contradicts. And NOOP does nothing when the fact adds no value. No separate classifier, the language model makes the call. The paper's second architecture, Mem0 graph, stores memories as a directed labeled graph. Entities become nodes, like Alice or San Francisco, each with a type, an embedding, and a timestamp. Relationships become edges, so Alice lives in San Francisco is a triplet connecting 2 nodes. When new information conflicts with an existing relationship, a conflict detector flags it, and an update resolver marks the old edge invalid instead of deleting it, which preserves the timeline for temporal reasoning. The reference implementation runs on Neo4j. Part 2. Installing Mem0 and configuring a fully local, GPU-accelerated stack. Installation is one line. Pip install mem-zero AI, or use UV for faster resolution inside a virtual environment. For the best retrieval quality, add 2 optional packages. Spacy powers entity extraction, and fastembed enables BM25 keyword scoring. Together, they unlock Mem0's multi-signal search. If you want a local LLM, install the Ollama client too. The simplest cloud path just needs an OpenAI API key exported in your shell. Here is a real install on this machine. The editable SDK plus sentence transformers and Gradio resolve in seconds with UV. The key detail is at the bottom. Torch 2.1 with CUDA support, and the GPU verification line confirming the RTX 4090 is visible. Always install the CUDA build of Torch first, so nothing drags in a CPU-only wheel afterwards. Everything in Mem0 is a provider you can swap. A config dictionary has 3 main blocks. The LLM block decides who extracts and consolidates facts. Here, a local Gemma model served by Ollama. The embedder block turns text into vectors. Here, a small BGE model running on CUDA. And the vector store block says where memories live. Here, a Qdrant server on localhost. Pass the dictionary to memory.fromConfig, and the pipeline is wired. And here is the smoke test on the same machine. One add call distills a sentence about diet and hobbies into 2 clean memories in about 3 seconds on a local model.
The search call then answers a dinner question in 1/100th of a second with relevant scores attached. Notice the embedder device line. Everything ran on CUDA 0, no cloud calls anywhere.
Part 3. What the research shows, and how to actually use mem-zero in your own applications. The paper evaluates on LoCoMo, long multi-session conversations with 4 question types, against 10 baselines, including MemGPT, LongMem, ZEP, and OpenAI's built-in memory. Mem-zero takes the top LLM as a judge scores on single-hop and multi-hop questions, and the graph variant leads on temporal reasoning. Overall, that is a 26% relative improvement over OpenAI's memory feature. Accuracy is only half the story. Production systems live and die by latency. Feeding the entire conversation to the model tops the quality chart, but costs 17 seconds at the 95th percentile. Memo answers in 1.4 seconds, a 91% reduction, while saving more than 90% of the tokens. Search itself takes 150 milliseconds at the median. That is the trade Memo makes, near full context quality at a fraction of the cost. How much does a memory store actually cost in tokens? For an average LoCoMo conversation, Mem0's dense natural language memories occupy about 7,000 tokens. The graph variant roughly doubles that to 14,000 to pay for nodes and relationships. The raw conversation is around 26,000, and ZEP's graph, which caches a summary at every node, inflates beyond 600,000 tokens, more than 20 times the raw text it represents. Compact memories are not just cheaper, they are faster to construct and available within a minute. The research kept moving. In April 2026, Mem0 shipped a redesigned pipeline. Extraction became single pass and add only. One LLM call, nothing overwritten. Facts confirmed by the agent itself are stored with equal weight. Entities are extracted, embedded, and linked across memories. Retrieval fuses 3 signals in parallel: semantic vectors, BM25 keywords, and entity matches, with time-aware ranking on top. The scores jumped accordingly: 92.5 on LoCoMo and 94.4 on LongMemEval. Here is the whole Quickstart. Import memory and instantiate it. With defaults, it uses OpenAI and a local Qdrant. Call add with a message and a user ID. Mem0 extracts the facts for you. Later, call search with a question and the same user ID inside filters, and you get back scored memories ready to drop into a prompt. 6 lines, and your agent remembers. The add method takes more than strings. Pass a whole message list with roles, so user and assistant turns are distilled together, and facts the assistant confirmed get captured too. Attach metadata, like a category or source. It is stored alongside the memory and filterable later. Scope with user ID, agent ID, or run ID. And if you already have clean facts, set infer to false to skip extraction and store them verbatim. Search is where the current API differs from older tutorials. Entity scoping now lives inside the filters dictionary. Passing user ID at the top level raises an error. Filters support rich operators: greater than, in, contains, and logical and or, so you can slice memories by metadata precisely. Tune top K for how many results you want. And remember, there is a default score threshold of 0.1. Results scoring below it are dropped, which is why a strong embedder matters. Beyond add and search, memories have a full lifecycle. Get all lists everything for a scope, handy for a memory browser. Update rewrites a memory by ID when the user corrects a fact. History shows every version a memory went through: adds, updates, deletions, with timestamps. Delete removes one memory, delete all clears a user, and reset wipes the store. Each memory keeps its ID, so your app can manage them like records. Agents are asynchronous, and Mem0 ships a native async client. Import AsyncMemory, and every method, add, search, get all becomes awaitable. That lets a chat handler kick off memory writes with async.io create task without blocking the reply, and fan out several searches concurrently with async.io gather. Same providers, same config dictionary, just non-blocking end-to-end. Nothing in Mem0 requires the cloud. This is the exact stack running on this machine. Ollama serves Gemma as the extraction brain. Sentence Transformers computes BGE embeddings on the RTX 4090, and a Qdrant container holds the vectors. Point the Hugging Face cache at a big drive, set device to CUDA, and the whole memory pipeline, extraction, embedding, storage, search, runs offline. Your user's memories never leave the box, and the marginal cost per memory is 0. To see it end-to-end, we built a small Gradio demo against that local stack. One tab is a chat, the other is a memory browser where you can list or wipe everything stored for a user ID. The header says it all: a local Gemma model, BGE embeddings on the 4090, and Qdrant behind it. About 100 lines of Python, and the model loads once at startup. And here is the payoff. Earlier in the chat, the user said they are vegetarian and avoid dairy. When they later ask what to cook for dinner, the assistant proposes a dairy-free recipe, and the footer lists exactly which memories grounded the answer with their relevance scores. The vegetarian preference came back at 0.44. That transparency, which memories were used and how strongly, is gold for debugging agent behavior. Every memory-augmented chat reduces to one loop. When a message arrives, search memories for that user. Inject the hits into the system prompt as context. Generate the reply with your LLM. Then add the user and assistant turns back into memory, so the next question benefits. Search, inject, reply, remember. 4 steps you can wrap around any model or framework in an afternoon. If you would rather not run infrastructure, the hosted platform mirrors the same API. Swap memory for memory client with an API key from the dashboard, and add, search, and get all behave the same, while extraction, storage, and scaling happen server-side. The platform runs the latest memory algorithm with proprietary optimizations, ships analytics and a memory dashboard, and there is an async client as well. Prototype locally, then switch classes when you want managed. Graph memory from the paper is one config block away. Add a graph store section pointing at Neo4j or Memgraph. Kuzu and Apache Age are supported too, and Mem0 starts extracting entities and relationships alongside vector memories. Reach for it when your questions span connected facts: who works where, what happened before what, how people and places relate. For plain preference recall, vectors alone are faster and cheaper. The paper is explicit about that trade-off. Mem0 gives you 3 identity levels, and choosing well keeps memories clean. User ID is long-term personal memory, preferences, history, facts that should survive forever. Agent ID scopes knowledge to one assistant, useful when several bots serve the same person but should not share notes. Run ID is scratch memory for a single session or workflow, perfect for multi-step tasks and easy to wipe afterwards. They combine freely, and every search filters on exactly the scope you pass. Picture a support bot. A customer wrote in last month about a billing glitch on the Pro plan and mentioned they are on Android. All of that became memories. Today, they just say, "It is happening again." The bot searches, retrieves the old ticket context, the plan, the device, and answers like a colleague who was there. No 20 questions, straight to a fix. Resolution gets faster, and customers stop repeating themselves, which is the single biggest complaint about bot support. The paper calls out domains where continuity is the product. A tutoring agent remembers that fractions clicked last week, but word problems did not. So today's session starts exactly at the frontier of what the student knows. A health companion carries forward medication routines, allergies, and how symptoms evolved across months of check-ins.
In both cases, the value is longitudinal. The agent is useful because it has been there for the whole journey, and that requires memory that outlives any single context window.
Memo is bigger than one SDK. There is a TypeScript SDK with the same two flavors, hosted client and self-hosted memory. An MCP server brings memory tools to Claude Code, Cursor, and any MCP-capable editor, with a plugin that captures memories automatically as you work. OpenMemory is the self-hosted platform with a web dashboard. There are command line clients in Python and Node, a REST server image for Docker, and a Vercel AI SDK provider for the JavaScript ecosystem. One memory layer, reachable from wherever you build.
So, when do you use what? Memo memories answer in about a second and a half at the 95th percentile, using a couple of thousand context tokens, and quality lands within a few points of full context, with cost staying flat as history grows. Add the graph only when queries are genuinely relational. Full context wins the benchmark by a hair, but at 17 seconds and ever-growing bills, and it simply breaks once history exceeds the window. Plain RAG over conversation chunks is cheap but noisy, plateauing around 61% on the judge metric. For short-lived tasks, that can still be fine. 5 things to remember. Memory is not the same as context. mem-zero extracts, consolidates, and retrieves instead of replaying transcripts. The two-phase pipeline lets the LLM itself decide whether each fact is an add, an update, a delete, or a no-op. You get 91% lower tail latency and over 90% token savings compared to stuffing the full history. Scope everything with user, agent, and run IDs and pass them through filters in search. And you can start completely local and free with Ollama and Qdrant, then move to the hosted platform when you need scale. Thanks for watching. Links and credits are up next.
If you like this video, please subscribe and share. Thank you.